All right, hello. I shouldn't have crossed out this entire notes last time because we didn't quite finish it for the emission spectra. We've still got a little bit left here, but keep this open if it's helpful. Otherwise, this video, we're gonna switch over to crunching noises, sorry. We're gonna do homework 3.4, the Bohr model of hydrogen. So here's what that homework looks like. Here's the top portion. Specifically, we're dealing with the element hydrogen, the most simple element on our periodic table. It has one proton, one electron, and it's just so simple because it's just one electron. So that'll be helpful for doing this assignment here. So looking at the picture, this is showing all of the different transitions that one electron, hydrogen has one electron. Little lonely boy. Real sad. So hydrogen only has one electron. And these are all of the places that it could drop from. It could be in ring 2 and drop to ring 1. That's the transition that's showing in part A, right? Ring 1, ring 2, drop. So down here in the table, you'll put emission for line A is a drop from 2 down to 1. I think down below I wrote like the whole thing, like from n equals 3 to n equals 2, but I'm just going to keep it simple. We went from ring 2 to ring 1. Line B is going from the 3rd ring down. This whole section here, all of these are dropping down to ring 1. So we've got 2 to 1, 3 to 1, 4 to 1, etc. And this is called the Lyman series. Finishing this out, 5 to 1, 6 to 1. The next one, where they all are ending here in ring 2. This one is called the Balmer series down below. This one is from 3 to 2. Line N is dropping from 4 to 2, 5 to 2, 6 to 2. So you can keep going and finish out the drops. And what I've filled in for you here is I've given you the wavelength of the drops. The one I want to focus on first is the Balmer series, the drops that end at level 2, because those ones were significant in the notes. The ones that ended at ring 2 are the ones that humans could see, these 4 right here. So the wavelengths that we used are the same ones that we've got going on here. 656 nanometers. If you want, you're welcome to use a calculator to convert, but I know that a 3-digit number in nanometers is just going to be the decimal form to the -7th power meters. So we're just converting nanometers to meters. And the 656, that was the one that corresponded to red. If we didn't have our notes with us, you could still figure that out just from the homework by looking up here at this chart of the electromagnetic spectrum. So the wavelength was, what did we say, 656. So over here, this is wavelength, 650, like there is like the red one. The other ones that we've got going, the 486. 486. That bluish green light cyan color. Let me go take care of my dog 1 second. Okay, so looking back here, these are the 4 colors we see. You can tell what colors they are corresponding to up here. And I'll do some of this with you, but not all of it. The next one is going to be 486, 4.86 times 10 to the negative 7 meters. This is the visible region. It's specifically the cyan color. To get the frequency from wavelength, go back in your notes a few pages, back, till we've got this one here. It's on the transverse waves page, and it's down here at the bottom. Speed of light equals wavelength times frequency. Always plug in 2.998 times 10 to the 8 meters per second for C. So to get from here to here, we put the equation at the top. Speed of light, which is that number, equals wavelength times frequency. So the first one's already been done for us. The second one here, I'm going to divide over the wavelength. 2.998 times 10 to the 8th power divided by 4.86 times 10 to the negative 7th power. The frequency of this one is 6.17 rounding times 10 to the 14th inverse seconds. So you'll do the same for these 4. Again, these 4 are the only ones that are going to be in the visible region. And the question is, what about the rest of them, like the Lyman series? The Lyman series is the one that has the biggest drops. Big drops means more energy. So if I was just going to guess, you know, they are going to be in the higher energies, this, right? As we get more and more this way, you get higher energy. Whoops. And down here, this one is lower energy. So if this is the region we can see because of Balmer, Lyman, I'm thinking it's like, whoop, going to be kicking up higher. So doing a couple of these ones. I don't know. Let's do A and E just for a comparison. So A is pretty similar. We have a 3-digit number. I'm going to convert it. 1.22 times 10 to the negative 7th. Really quick, let me just figure out the radiation type from 122. This is 400. And this is 10. Then 122 is somewhere in between those. So that's ultraviolet, radiation type, ultraviolet. We can't see it. And that's where all of these are going to be, right? 103, 97, 95. 94. They all fit between 10 and 400 nanometers. So while I'm at it, let me just do UV, ultraviolet. And the frequency will be the speed of light here. Whoops, let me get that glare off the screen. Speed of light divided by 1.22 times 10 to the negative 7th. 2.46 times 10 to the 15th inverse seconds. 94 is not a 3-digit number, so you have the choice. You can either do it the long way and take 94 divided by 10 to the 9th power and get your answer. Or here's my cheater way. Just make it a 3-digit number, right? 94094. Now it's a 3-digit number. And I can do an improper scientific notation. 0.94 times 10 to the negative 7th, which is the exact same as 9.4 times 10 to the 8th. I promise it is. Watch. It just fixes it for me. So that's my little cheater method. And if I were to, oh, someone's at the door. It was the IKEA person. They delivered my furniture. Yay. Okay, good barking, Archie. Keeping everybody safe. But now it's video time. So back to this. Is this the right one? Yeah, okay. So this one is 3.19 times 10 to the 15th inverse seconds. And last one I'll do with you, I'll do one from this next series, the Paschen series, although my personal favorite is the Pfund series. It just is like a fun name. Pfund. I'm sure you don't say it that way. But well, actually, yeah, I'm just gonna do the Pfund. Nah, I don't want to. It doesn't really matter. All of these ones are just low energy ones. We don't really talk about the bracket series or the Pfund series. The ones that are pretty much major are the Lyman series, the Balmer series, and Paschen series is in infrared. So for Paschen, line Q is from 4 to 3. 1875 nanometers. Again, you can do it the long way. You can say 1875 divided by 1 times 10 to the 9th. You can do that. That works. Or similarly to how I added a 0 to make it a 3-digit number, in my mind, I'm playing pretend that this only has 3 digits. And if it was 875, then it would be 8.75 times 10 to the negative 7. And I'll just sneak that one in where it goes. I promise it's the same. Works every time. 18.75 times 10 to the negative 7. Improper fraction converts to proper fraction. Up to you how you want to do that one. I'm okay with either. And then we'll take the speed of light divided by that. The frequency is 1.60 times 10 to the 14. 1875 corresponds to the whole rest of the chart here, all the way that we're just going to focus on there. It's going to be infrared. So your task will be to fill in the rest of this table. And then the questions below, which energy transition above would have the highest associated energy? So which of these lines out of all of them, A, B, C, D, E, M, N, O, P, Q, R, S, all of them. The one that has the biggest energy is going to be the one that traveled the farthest. And that's line E. Line E is the greatest distance. And that's what you're going to say when it's explain your reasoning. The farther that the electron falls, the more energy that's going to be released in that transition. So describing in terms of electron energy states and energy changes, how hydrogen's bright line spectrum is produced. This is from the notes. It's saying, based on the drops, based on the drops and the electrons dropping, how do we get this barcode? The barcode, stripe. The barcode is what they're calling bright line spectrum. So maybe in the notes you can label it, this is the bright line spectrum, but I like to think of it as a barcode. Because although we haven't talked about it yet, every element has its own unique little barcode. The one for hydrogen is this. The one for helium is this. So just like at the store, you go beep, beep, scan, scan, and all the products come up with a barcode. Different elements have different barcodes. So for here, you're going to say something like the amount that it drops corresponds to the energy that it has. The energy corresponds to its wavelength. The wavelength, when written out, will look like a barcode, aka bright line emission spectrum. So there's the answers to those. Once you're ready, on the back side here, this is exactly what we were talking about. Here's the barcode. Here's the colors. Sorry, not the colors. Here's the one that we can see as colors. And just really quick, number 6, label the Paschen, Balmer, and Lyman series. Lyman series is the one that ends at ring 1 here. Balmer ends at ring 2, and that's what you can use to figure out this. It's not written in a curve. They've got the rings sort of straight, but you can see, okay, this one, these ones are still Lyman because they're ending at ring 1. Balmer ends at ring 2. Paschen ends at ring 3. The other 2 series have been omitted. Okay. Label which 4 spectral lines would have been visible. That's the Balmer series. Label them the appropriate colors. The tiniest line is our lowest energy color, which is red. the biggest drop is our most energetic color. And the other two are somewhere in the middle. Label which 3 lines would have been emitted as infrared. You can't see infrared. And which 5 would have been ultraviolet. Too high energy for us. The Bohr model, aka this idea that the electrons are moving up and down in the rings, was able to account for all of the spectral lines of hydrogen mathematically. This is what was on the front side of the homework. Every single line that was drawn, we were able to do math on to figure out the colors and such. So why then, why we don't do any other, we don't really look at any other ones other than hydrogen. The question is why? Why might the spectra of atoms with more than one electron be difficult to explain using the Bohr model? So you're going to put your answer here, but basically look at this. This whole page, all of this nonsense is over hydrogen, the simplest of elements that only has 1 electron. How in the world are you supposed to do any other calculations for anything else that has more than 1 electron? It would just be absolute insanity and complication. So you only will ever have questions like this one based off of hydrogen. So, so far we've completed all of the first page and a little bit of the back side. We're gonna be kind of just going back and forth between the notes. So that's it for this video. But I will do the rest of the homework with you in a separate video. So don't panic and start working on it yet. I'm just gonna get another video started. I want to finish up the notes first.